has an associated energy. As an object gains energy by moving at speed, its mass actually increases. The metal balls on this office toy weigh more when they are moving than when they are at rest. But because they are moving slowly, the increase in mass is very small. If they were moving at close to the speed of light, the increase in mass would be immense. In fact, a subatomic particle whizzing around the CERN accelerator close to the speed of light can weigh more than 7,000 times its weight at rest. As the particles get heavier, scientists at CERN must provide more and more energy to keep them moving.
As you increase the energy of a particle, you get closer to the speed of light. And then you double the energy and you get a little closer. And then you double the energy and you get a little closer. But you never go beyond. In order to reach the speed of light, you would need an infinite energy, which we happen not to have available.
If energy is the stumbling block of subatomic time travel, then imagine the scale of the problem for a human-sized time machine.
The main problem with using speed to time travel is that we can't move an object anywhere near to the speed of light. It would take all the Earth's energy resources just to push our rocket to a tiny fraction of the speed of light. But you wouldn't notice any difference unless you got very close to the speed of light itself. We simply don't have enough energy.
And there's another problem. Using speed to build a time machine is a one-way journey into the future. Traveling close to the speed of light will enable time travel to the future, but the time traveler has not mastered time. He has merely slowed down his own rate of time and fast-forwarded himself through time. He wouldn't be able to come back to tell his tale. There is, however, another way to build a time machine. Gravity. Many of us think of gravity as simply a force that keeps us on Earth. But scientists here at Manchester University in England view it in a totally different way. For the time traveller, gravity is evidence of how mass bends or distorts the space-time fabric. Professor Brian Cox is an expert on gravity and on how it interacts with space-time.
Space-time's not just, up there, it's here, it's in front of me and it's inside me. And I bend and curve it a little bit. I produce a little bit of gravitational force. But of course, I'm very light, so when I move, I don't curve it very much. But something the size of a star or a galaxy or a black hole warps and curves the space-time a huge amount.
The greater the mass of the object, the greater the impact or dent on the space-time fabric. This isn't just in theory, here's the evidence. These Hubble telescope images show what is happening to light as it travels through space. As light passes a galaxy, its path bends. By examining how light bends as it travels, we can prove that mass is bending space-time. This experiment replicates this phenomenon in a lab. It's a mini-universe, and it shows how light travels across space-time. In flat space-time, a light beam follows a straight line. But there is evidence that light is bending as it travels through the universe. The path it follows must also be bending, and that path is space-time itself.
Billions of stars are bending the space-time, acting like a lens. So a lens curves light, and if you bend the space-time, the light will curve. So you get the image of the galaxy in the middle, but then you get these really distinctive rings around. And that's strong evidence, overwhelming evidence, that mass bends space-time.
This warping of space-time will help us to build our time machine. When gravity bends space-time, it has a very real effect on how time passes. Here on Earth, we might not feel it, but time runs slower on the ground floor compared to at the top of a skyscraper.
The closer I am to the Earth, the more curved the space-time, the stronger the gravity, and the slower time ticks. Whereas here, space-time's a little bit less curved, gravity's weaker, and so time ticks faster. Now, it's a really tiny effect. If I was to stand at the top of this building for 100 years, then my watch would be 50 millionths of a second faster than somebody's watch down on the ground. So in a sense, the Earth is a time machine.
Take this into space, and the effect is even greater.
Yeah, I'd like to go to the university. It's M199QL. The fact that time passes at a different rate in orbit a long way from the Earth than it does at the surface of the Earth is really important for GPS or sat-nav, because that works by having synchronized clocks on the ground and in the satellites. And because the satellites are in a weaker gravitational field, time is passing more quickly. And actually, there's a time difference of 50 microseconds a day, which is 50,000 feet a day. So if you didn't correct for that and didn't take account of the fact that time passes at different rates, satellite navigation wouldn't work.
Earth's gravity and consequent warping of space-time isn't extreme enough to help a time traveler journey into the past. But there are places in the universe where gravity dramatically distorts space-time.
Most of space-time is nearly flat. It is only in black holes that it is strongly warped.
Professor Stephen Hawking is renowned as a world expert on black holes. Back in the 1970s, his groundbreaking research illuminated the then theoretical black hole. The gravitational pull of a black hole stretches and warps space-time around it to an incredibly deep cone-shaped hole. Because the gravity of the black hole is so intense, it drastically slows down time. Physicists like Hawking are fascinated by what a black hole does to time, but there is a catch. The black hole has a boundary called the event horizon, which leads down to the densest point, the singularity. Not good news for the time traveler.
In a black hole, you would be bound to hit the singularity and be crushed out of existence.
This is the Chandra X-ray Observatory. It's located 200 times higher than the Hubble telescope, and it provides scientists with new data on black holes.
Thank you, sir.
The mirrors on board this satellite are the smoothest mirrors ever constructed. Chandra sends back X-ray images 10 times sharper than the best previous X-ray telescope.
82 EPS.
That's the equivalent of reading a stop sign from 19 kilometers away. When scientists analyzed X-ray images of supermassive black holes, they discovered that they were spinning at close to the speed of light. This causes the space-time fabric to be dragged around. Scientists call this frame dragging. Space-time becomes so distorted that it forms an almost complete circle. Confirmation that black holes rotate was music to the ears of anyone interested in time travel. The time traveler was just about to strike gold.
I think I and other people that are working on this would feel like pioneers in the field of time travel.
So convinced is Gott that time travel will one day be possible, he'd volunteer himself as a guinea pig.
I guess it'd be worth the risk.
Gott is one of the few physicists in the world who claims to have found a solution to voyaging back in time. He figured that the secret to building a man-made time machine was to take inspiration from the universe and then copy it.
One place to look for a naturally occurring time machine would be in the center of a rapidly rotating black hole.
What intrigues Gott is how the rotating black hole warps space-time around it. Gott is a professor of astrophysics here at Princeton University. He searched the universe to find anything that could warp space-time as much as a rotating black hole. What he found led him to make a bold and ambitious hypothesis, which is based on something that is still theoretical. It's called a cosmic string.
Cosmic strings are thin threads of energy that are left over after the Big Bang.
Despite being no wider than an atom, cosmic strings have colossal density. A string just 1 meter long would exert more gravity than the Earth. Immense gravity warps space-time. With his eye on time travel, that means one thing for Richard Gott.
Please enjoy your meal.
Thank you very much. I found out that because of the warping that the strings do in space-time, that if two strings, infinite strings, were passing each other at high speed like this, you could use them to make a time machine.
The fast-moving strings warp space-time as they pass, so that they bend it down into a wedge shape. Normally, a spaceship would have to take the longer route across space-time. But the time traveler can now take the shortcut. By outrunning a light beam, he can travel back in time. If this car were a huge spaceship, and God could find two cosmic strings, he could return before he departs. The space-time around the two moving cosmic strings is so twisted that God can circle the strings and come back before he sets off. Here's how. Cosmic strings bend space-time and provide a shortcut. By journeying around the strings, God travels faster than light does across normal space-time.
You can't build a rocket that goes faster than the speed of light, but with curved space-time, you can take a shortcut and beat the light beam and theoretically make a time machine in principle.
The path of time is no longer linear. Instead, it forms something like a circle. There is, however, a small hitch. Cosmic strings are not only purely hypothetical, they're also elusive.
We wouldn't expect you to be so lucky as to find two infinite cosmic strings passing each other at the speed required to make a time machine.
God navigates this strings problem with a hypothetical alternative. Cosmic loops. They too may sound far-fetched, but the skeptics could find no fault in Gott's theory.
Well, it certainly created a hubbub because many skeptical people might wonder whether you could actually do such a thing, but here was an exact solution of Einstein's field equations that allowed time travel into the past.
Richard Gott's time machine does, however, have a weak link. He discovered that at the very moment he warped space-time enough to form a circle, the whole region would fall inside a black hole.
And that's not good because a black hole, well, that's a hotel where you check in, but you don't check out. So it looks like the time travel region would be trapped inside a rotating black hole.
Even if the prospect of being crushed out of existence doesn't deter the time traveler, Gott's time machine has another limitation.
The string loop solution, if you wanted to go back in the past a year, it would take a mass of about half the mass of our galaxy. You'd have to manipulate a mass that large. So you'd have to be one of these galactic civilizations that had the energy resources of the entire galaxy at your command. So this is well above the current NASA budget.